Okay. Yeah, so thank you very much, Kati, for having me here to speak. And hello, everybody. So as Kati said, the title is the general Calderón problem on Riemannian surfaces and inverse problem for minimal surfaces. So there are two topics. I will mostly speak about inverse problems for minimal surfaces, but I will as well announce new results regarding the general Calderón problem on Riemannian surfaces. So these are separate topics, but they are connected to each other. You will see how. And this talk is based on joint works with Katalin Karstea, Matti Lassas, and Leo Zhou. And one of the papers is already in archive, and another paper should appear there soon. Okay, so let's start. And please ask questions if you have any. Just a second. I will have this toolbar now somehow. No, all right. So let's start what happens in Euclidean space. So there are several ways to define minimal surfaces. A minimal surface which is embedded to Rn plus 1 and which is given as a graph of function u. Then the graph of u is a minimal surface if u satisfies the minimal surface equation, which you see here. So it's some kind of divergence form equation. It's non-linear and it's of second order, meaning that it has derivatives up to order 2. More precisely, this equation is quasi-linear elliptic. So this means that the principal part, meaning the second order derivatives of this equation, is linear operator and it's elliptic, meaning it's like Laplace type. And quasi-linear means that the components of this equation, where we have derivatives up to order 1, can be non-linear. If you linearize this equation at u is 0, you will see that actually the principal term is just the normal Laplacian in Rn. The feature of minimal surfaces is that they have vanishing mean curvature. So for those of you, this will notation make sense. So it's the trace of this tensor when you have inner product of covariant derivative to direction x of normal vector field n, inner product with y. This kind of the trace of this should vanish. So x and y are here tangents and is normal to the surface. If you don't know what this notation means, don't worry. More generally, a minimal surface embedded in n plus 1 dimensional Riemannian manifold M and G bar can be defined to be an n-dimensional submanifold whose mean curvature vanishes. Okay. So now you know what is a minimal surface equation in Euclidean space, but how do the minimal surfaces look like? So unfortunately, the great Simons passed away some weeks ago, and I was thinking that maybe this is a good place to let Mr. Simons explain what are minimal surfaces. And let me try to show you a video. Let's see how this goes. So, sure. Just a second, I try to get the video somehow working. Okay, so do you see Simons now? If not, please tell me. So what are minimal surfaces?
Does any of you know what a minimal surface is? Well, someone must know what a minimal surface is. Okay, so a minimal surface is a surface of minimal area with respect to its boundary. So imagine taking a wire frame, just a closed frame, dip it in soap suds, and then take it out, and there'll be a film that is bounded by this thing, and that film, that soap film, has less area than any other surface with that boundary. So that's a minimal surface. And the first Fields Prize winner back in maybe 1905 had proved that any such boundary would have a minimal surface, just one, and it would be smooth. It wouldn't have any points or anything like that. It would just be a nice, smooth surface. And as I said, he won the Fields Medal for that. And so I got interested in that area.
Okay, so now you know what are minimal surfaces. So I'll go back now to the slides. And now you should see the slides. There's some kind of chat now, but I cannot answer that. So if you don't see the slides, please let me know. You can see the full video of the SimCMOS presentation from this link later after the talk if you want. Then some examples of minimal surfaces. So even in the Euclidean space R3, the class of minimal surfaces is quite rich. So here on the left, you see something which is called Schwarz D surface. So it's some kind of, it looks symmetric somehow. It's a little bit hard to figure out what it actually looks precisely, at least to me. But if we believe Simons, it's a smooth surface and it's somehow symmetric from the picture. Here on the right, you see something which, at least to me, it's more easy to visualize. So it's some kind of symmetric, nice, smooth surface. The feature of both of these pictures is that they are topologically non-trivial. Okay, then we go a little bit deeper into the business. And for that, I need to set up notation and also define coordinates where to work, a convenient set of coordinates. So from now on, I will only consider the case where the dimension of the surface is n is 2. And I will work in Fermi coordinates relative to a two-dimensional surface here, omega, which is embedded in three-dimensional manifold M. So throughout the talk, the three-dimensional manifold where things will be embedded will be M, and the metric on it will be G bar. In Fermi coordinates, the three-dimensional metric G bar looks like this. So it has two parameters, S, which belongs to an interval in the real line, and X is a coordinate or a point on this two-dimensional surface omega. And the metric formula is this. So it has ds squared, so it's flat in this I direction in that sense. And here in the latter part contains one parameter family of metrics parameterized by S on this surface omega. Fermi coordinates always exist, so using this is not a restriction of generality. And this, by using these coordinates, we may view this three-dimensional manifold M locally as I times this surface omega. If you know what are boundary normal coordinates, then you will see that this form of the metric is exactly as the form of the metric in boundary normal coordinates. About notation, the two-dimensional metric during this talk will be G without the bar, and from this Fermi coordinates formula, G is given by these GKL components, so the matrix components, when you put S to 0. So GKL 0x are the components of the G, 3D metric G. And also for the next slide, I need this notation, and it's only in the next slide, I think. So if you use a function over this surface omega, I write GUX is G, where I have put in place of S is UX, and then I have the X as well in the argument. In the next slide, I will have the minimal surface equation in general, and you will see that the equation will depend not just only on the metric 2D metric G, but also on the 3D metric G bar. And the reason for that is that if we define minimal surfaces as surfaces for which the mean curvature vanishes, this mean curvature depends on the 3D metric. So what is the equation? So this equation is for minimal surface embedded in three-dimensional Riemannian manifold M G bar. If a minimal surface is given as a graph of a function U over a two-dimensional surface omega, then the graph is a minimal surface if U satisfies in the Fermi coordinates the following equation. So the equation, as you see, looks a bit complicated. So let me try to walk you through that. So it has two components. The first one is something which looks a little bit similar to what we had in the Euclidean space. The only difference to that is that we have some kind of coefficient matrices inside. But this equation also has a different part, an additional part, which is FU gradient U. And the FU gradient U, it has this kind of formula, which you see here. In this formula, double dots are the Euclidean gradient and inner products. So as I said, if U solves this equation, the graph of U is a minimal surface. And the equation, you probably agree, it's a little bit complicated. You do not need to remember it after this. I just wanted to show you that what kind of object we are dealing with. Since the equation is quite complicated, the related computations in the minimal surface business, they are quite long. And it's a typical feature of the papers which consider minimal surfaces. And this equation is invariant under isometries of this three-dimensional space mg bar. By the way, I will sometimes call this three-dimensional space the ambient space. However, this equation is not conformally invariant in dimension 2, which means that in the inverse problem, there is hope that we can recover things up to an isometry and not just up to a conformal mapping, as sometimes, maybe often is the case in dimension 2 that you can recover things only up to a conformal mapping. But here, there's hope to recover up to an isometry. Okay, so let's then define the Dirichlet-Neumann map. So from now on, I will only consider minimal surface, which are given as graphs over a surface omega. And now I will make this kind of additional assumption, or I will set this omega itself to be a minimal surface sigma. This is a technical thing to do. It's not necessary, but it makes things easier. So from now on and throughout the talk, the minimal surface will be sigma and G without the bar. So this is a two-dimensional Riemannian surface. Given this minimal surface sigma, the Dirichlet-Neumann map is given by the usual assignment. How? Well, you take a boundary value f for the minimal surface equation, which you saw in the previous slide. Then you solve the minimal surface equation to get the solution, which is UF. And from that UF, you compute its normal derivative on the boundary. So that gives you a mapping from boundary functions to boundary functions. It's the usual way to how to define a Dirichlet-Neumann map. Here f is small, and the reason why f is small is that you want to solve the minimal surface equation, and that can be shown to be possible if f is small by using the usual implicit function theorems, theorem in Banach spaces or contraction method. An interesting fact about the DN map of the minimal surface equation is that it is actually also determined by just areas of minimal surfaces. To see that, it's relatively easy exercise in calculus of variations, and that's because minimal surfaces minimize this kind of functional. So how to get the DN map from this functional is that you vary this functional in the set of functions solving the minimal surface equation. It's very easy, and we can think about that since it's equivalent to having the DN map for areas of minimal surfaces. The latter is somehow like purely geometric data. Okay, so I now define what is the inverse problem for minimal surfaces. And there are two equivalent formulations. So I will now formulate the problem in two equivalent ways. In both of these formulations, I will assume that the two-dimensional minimal surface sigma G is embedded in three-dimensional Riemannian manifold MT bar. So first, the DN-map formulation. Well, assume that the Dirichlet-Neumann map, which we had in the previous slide, of the minimal surface equation is known. The task is to determine sigma and the metric G, which is induced from the three-dimensional metric MG bar on this sigma. So determine sigma G. Area data formulation, which I like to call it purely geometric data. And it goes as follows, so this equivalent way. Assume that the area of a minimal surface sigma, which you try to find, an area of its nearby minimal surface perturbations are known, and the task is the same. Determine this Riemannian surface sigma G. This Riemannian surface sigma G is also a minimal surface. In both of these cases, as I told you, the equations are invariant under isometries, so the determination will be at best possible after an isometry. When we go to this, how to prove these things or study these problems, we will actually find also information about the 3D metric as well. So that is an interesting fact going forward. I will maybe explain in the end. And please ask questions if you have any. So next I will explain our main results, and there will be two types of main results. The first one will be for the minimal surfaces, and the other one will be about the about the Calderón problem for linear operator, the Schrödinger operator, as you will see. So the first main result about the inverse problem for minimal surfaces, it goes as follows. So it's a result by Katalin, Karsten, Matti Lasses, me, and Leo Zhou. And one of these papers, it's from 2023, and the second should be out soon. And combining these works, we have the following. So let's take two copies of our system. So we have sigma 1, G1, which is embedded in a three-dimensional M1, G1 bar. And likewise, we have sigma 2, G2, embedded in M2, G2 bar. So these sigmas are 2D minimal surfaces embedded in 3D manifolds M1 and M2. I assume that the boundaries of the sigma 1 and sigma 2 are the same, no sigma. I will assume boundary determination. We'll a little bit comment that a little bit later. Now, if the DL maps of the associated minimal surface equations satisfy the condition that for small boundary values, so small perturbations of the studied minimal surfaces, the DL maps agree, then it is possible to show that there is an isometry between these surfaces, sigma 1 and sigma 2. So isometric condition in geometric notation means this. So the pullback by F of G2 is G1. And an additional property of this F is that it's identity on the boundary. In addition, if we pull back the second fundamental form from, let's say, manifolds from the surface sigma 2, I will get that of sigma 1. So here eta 1 and eta 2 are the second fundamental forms of these minimal surfaces. So as you see, this result is general. There is no additional assumptions except this boundary determination. Why we assume this boundary determination is because in this business, you need to do quite a few boundary determination results, and they are not exactly the same. So it's quite obvious how to do those, but to actually write those things, it probably would be at least 10 pages, likely more. So it's just a little bit like we were lazy a little bit, to be honest. Right, so the recovery is up to diffeomorphism and not just up to a conformal mapping, as sometimes is the case in dimension 2. Also, the second fundamental form is recovered. And as I said, this second fundamental form depends on the 3D metric. So you will get some information about the 3D, the ambient space, MG bar. Now, so why do we work in dimension 2? Just there are several reasons, and one of the main reasons is that we need to solve the anisotropic Calderón problem at one stage. So as I think maybe all of you know, that the anisotropic Calderón problem in dimensions 3 and higher is basically almost completely open. So if you try to do this in higher dimensions, your progress will stop quite quickly. And many of the arguments in our work, however, works in all dimensions. Okay, then the other result. So basically this result, which I now will explain, it's an independent result. It will be applied in this minimal surface business, but in itself, it doesn't have to do anything with minimal surfaces. So as said, to solve the inverse problem for minimal surfaces, one must solve the anisotropic Calderón problem on Riemannian surfaces. In the case where both the metric and the potential are unknown, so we prove the following. This is the result which I will now announce. So this is a result by me and Leo Zhou, and it should be in archive hopefully in a few weeks. And it goes as follows. So let sigma 1 G1 and sigma 2 G2 be just Riemannian surfaces with mutual boundary. And now if the Dirichlet-Neumann maps of the Schrödinger equations, Laplace G1 plus Q1 on sigma 1 and similarly on sigma 2, if the DN maps agree, then there is a conformal mapping between these Riemannian surfaces, sigma 1 and sigma 2, which means in geometric notation that G1 is a conformal multiple of the pullback of G2 by this mapping J. And also this potential Q is not uniquely recovered, but it's only recovered up to this mapping J, but also one needs to scale the potential by the inverse power of C. So Q1 is C to the power minus 1 pullback of Q2 by J. So again, this as well is a general result. There is no additional assumptions, nothing. And you might wonder, can you improve the result to somehow take away this conformal factor C? The answer is no, because this problem has inherent conformal symmetry. Sometimes these symmetries are called gauge symmetries, so you only can recover things up to this conformal gauge. And how does this result relate to earlier results? So first of all, this result generalizes result by Oleg Imanuvilov, Günther Ullmann, and Masahiro Yamamoto from 2012. And they studied the same case on the complex plane, so on R2, meaning the topology is trivial. Then it also generalized a result by Colin Guillermo and Leo Zhou, 2011. In their case, the metric was unknown and only the potential was unknown. And this also generalized a result by Matti Lasses and Günther Ullmann, 2001. And in their case, the potential was 0, but the metric was unknown. And it also generalized results by other people as well. Any questions? Okay, so you might wonder, why do we study inverse problem for minimal surfaces? So there are some motivations, and one of the main ones is generalized boundary rigidity. And let me explain you next what that is. So in the generalized boundary rigidity problem, the aim is to construct a manifold from the areas of minimal surfaces. So remember that the areas of minimal surface determine the DN map. This is related to the usual boundary rigidity as follows. The usual boundary rigidity asks if a manifold is determined by lengths of minimal geodesics between pairs of points on its boundary. So note now that minimal geodesics are in fact 1D minimal surfaces. So instead of asking how to recover manifold from lengths of geodesics, we now ask how to recover manifold from areas of minimal surfaces. So in that sense, it's a generalization of that usual boundary rigidity problem. To the best of my knowledge, the first mathematical paper in this business was by Spiros Alexakis, Tracy Balehowski, who is here today as audience, and Adrian Nachman. And their paper was published in 2020, and they indeed asked the question, how to determine three-dimensional manifold from the areas of its minimal surfaces. Note now that in generalized boundary rigidity, the task is twofold. By knowing the areas of minimal surfaces, there are two things to do. First, recover the minimal surfaces, and then second, find a way to glue these two-dimensional minimal surfaces together to get the three-dimensional manifold. So you need to somehow stack up these 2D minimal surfaces to get the three-dimensional space. This above paper, it considered both 1 and 2 under some assumptions. In this talk, we only consider the first task, so how to recover the minimal surfaces. And as I said, it can be generally done. And how do we do this? How do we recover the minimal surface, individual minimal surfaces? Is by introducing the high-order linearization method for the problem. The generalized boundary rigidity itself is actually motivated by physics. There might be some other motivations as well, but one of the main ones is this ADS-CFT duality in physics, which I will now try to explain. I think there might be some physicists in the audience, so please don't laugh at me. So, an ADS-CFT duality conjecture in physics by Rui and Takayanagi states that so-called entanglement entropies of a quantum field theory living on the boundary are equivalent to areas of related minimal surfaces. So this is a quite popular paper by Rui and Takayanagi. It's from 2006, and their paper has thousands of citations. So this is just one conjecture in this ADS-CFT duality. The original paper about the ADS-CFT duality in general was by Juan Maldacena, and that is the most cited paper in physics ever. It has tens of thousands of citations. So this is a big field in theoretical physics. Now, let me try to explain what does this conjecture say about the conjecture by Rui and Takayanagi. So entanglement entropy, SA, is the experienced entropy of a physical system for an observer who has only access to a subregion A of a larger space. So what does this mean? So in some sense, you can think about this as some kind of conditional entropy. Then you don't have, it's a conditional measure of state of disorder that you don't have access to all places in your space. So maybe one example could be a black hole spacetime, where you don't have access to the states which are behind the event horizon. Now, physicists asked, well, they ask a lot of things, but one question which they ask is the following. Is a spacetime determined by entanglement entropies of a quantum field theory living on the asymptotic boundary? Now, this is equivalent by this duality of Rui and Takayanagi to the following question. Is a spacetime determined by areas of minimal surfaces which are anchored to the asymptotic boundary, to the asymptotic infinity? So you understand that this is now exactly the generalized boundary rigidity question. Can you determine a manifold from the areas of minimal surfaces? So what is the CFT in this CFT? So CFT is a conformal field theory, and that is a special type of quantum field theory. Interestingly, physicists actually give examples where the answer to the above question is yes. So by this equivalent characterization, especially they give examples where the generalized boundary rigidity problem is solvable. There are not many examples, but there are still few examples. And maybe our community can somehow help the physicist community in this aspect. Just shortly about the real situation in physics, if there's some people interested in this asymptotic business. The real physical situation is in the non-compact setting. And the typical situation is that you consider asymptotically hyperbolic Riemannian manifolds, and examples of such manifolds are time slices of anti-de Sitter space. So this anti-de Sitter is this ADS and this ADS CFT. Now you understand that if you consider things in some kind of infinite spaces, it's not very surprising that the areas of minimal surfaces become infinite. And this stems with the fact that quantum field theories have infinite degrees of freedom. So your data in this business is some kind of renormalized quantity of the areas. Mathematically, this is considered by conformal compactification. And when you compactify the manifold, the price you pay is that now the compactified metric blows up on the boundary. So it blows in a certain way when you approach. In this picture, this blue curve here. So this picture depicts the infinite manifold. So you put some kind of boundary curves to the infinity, and then you anchor a minimal surface starting from the infinity, which goes inside. And from the areas of these red curves, you try to figure out what is this empty bar. So exactly the generalized boundary rigidity. In this talk, everything will be compact and nothing blows up on the boundary. I just want to explain what is the real physical situation. Okay, before we go to the proof of the main theorem about minimal surfaces, let me give some earlier results by different people. So I already gave you some references, but let me give you more. So inverse problem for minimal surface equation, it started by when there was this paper by Tracy and Nachman and Alexakis, but after that there's a paper by Katalin Karste, Matti Lassas, me and Lauri Oksanen in 2022, and there we studied this kind of toy model. So in that case, the minimal surfaces were embedded in this kind of cylinder-shaped manifold. So sigma times r, so it looks like a cylinder. As it happens, in this case, the minimal surface, the inverse form of minimal surface is much easier. So it's in a sense some kind of toy model. About the same time, a little bit after that, Janne Nurminen from University of Jyväskylä, Finland, he proved the results for conformal Euclidean metrics in Rn about minimal surfaces. And some other, he studied also some other conformal cases as well. Physics papers about the construction of Riemannian manifold from areas of minimal surfaces in the context of ADS-CFT duality are, for example, by the following people. So this is Samuel Wilson. I think this is Ning Bao, maybe. This is Chung Yung Kao, Sebastian Fischetti, Cynthia Keeler, this is Veronica Hubli, she's quite famous physicist. And now a happy coincidence happens that actually this is Niko Jokela, who is from the same university as me, but he happens just accidentally to study the same problem just in the physics department. So now I'm collaborating with Niko at the moment. Arttu Pönni is also a Finnish guy. He's in the Aalto University, which is another university in Helsinki, Finland. The studies of inverse problem for nonlinear equations, it started from a paper by Jaroslav Kurulev, Matti Lassas, and Günther Ullmann in 2018. And they studied the nonlinear wave equation in Lorentzian spacetime. And that paper contained the idea how one can use nonlinearity as a beneficial tool. So a little bit after that, Ali Faiz Mohammadi, Lauri Oksanen, and at the same time and independently, Matti, Lassas, me, Yishuan Lin, and Mikko Salo, we figured out how to use nonlinearity as a tool for elliptic nonlinear equations, such as this nonlinear Schrödinger equation here. So after these results, there are a lot of papers regarding the elliptic case, when the principal part is something like Laplacian. There are results by Katja, our host, Ting Zhou, Yavar Kian, Ruyu Lai, Hongyu Liu, Leo, Xiao Lu, Bastian Harrat, Teemu Tyni, and later Potenciano Machado, and many others. So if you want your name in this list, please contact me after the talk. Okay, so let's then go to the proof of the main theorem. So the next slides will be a little bit heavy, and I will try to somehow guide you through and explain what is the main point. Right, so our task is to find a minimal surface from the associated Dirichlet-Neumann map. And the recovery of the minimal surface is based on the high order linearization method. And this high order linearization method was introduced in the paper by Jaroslav Kurlev, Matti Lassisen, and Winter-Ullman, which I had in the previous slide. So now let's consider 4 boundary values, fj, where j is now from 1 to 4. And let's consider solution to the minimal surface equation with 4-parameter boundary value. So the boundary data, or the boundary value for the minimal surface is epsilon 1 f1 plus epsilon 2 f2 plus epsilon 4 f4. I will denote epsilon this 4 double epsilon 1 to epsilon 4. So we consider 4-parameter family of solutions to the minimal surface equation. So the higher the linearization method, as the name somehow suggests, you start to linearize the solution and equivalent the equation. So now we take first derivative of the solution, u, depending on these 4 epsilon parameters, with respect to this epsilon j. So in that case, we denote dj, the epsilon j derivative of this solution u to the minimal surface equation. So now one can compute by just differentiating this messy minimal surface equation. You get that this dj now solves just the linear Schrödinger equation on the so far unknown minimal surface sigma. So now here, well, sigma is unknown, but especially g and the potential q are both unknown. Now, so what do we have now? So we assume that we know the Dn map of the original minimal surface equation, the nonlinear equation. So that means that we know the normal derivative of u here. Now, if you differentiate that normal derivative with respect to this epsilon j parameter, then you will actually get the normal derivative of dj. So that means from the Dn map of the minimal surface equation, you will get the Dn map of this linear Schrödinger equation, just by differentiating this epsilon j. Okay, so the other result which I gave you today was that we can recover a Riemannian surface and a potential q up to a conformal mapping from the Dn map. So since we know the Dn map of 1, this equals 1, we know g and q up to a conformal mapping. Just a note that, yeah, in fact, while this potential q is unknown, it also has an expression where you see it's minus the norm of second fundamental form squared and the normal component of the Ricci curvature. So this is the first instance where we see that we will also recover information about the 3-dimensional ambient space. Okay, so now we have recovered the minimal surface up to a conformal mapping, and we still have to recover the conformal factor. So let's go there next. So how do we do that? So we start to differentiate the solution u second time. So we start to recover the conformal factor by doing the second linearization. However, at this point, I will mention that actually the conformal factor will only be found from the third linearization. However, we first must solve the second linearized inverse problem to find a conformal multiple of the 2 times 2 matrix eta. Eta is the second fundamental form. So at this stage, we want to recover 2 times 2 matrix somehow. Okay, so we linearize. To do that, we linearize second time. And now I will denote by wjk the derivative with respect to epsilon j and epsilon k of the solution u, depending on the 4 parameters. And u solves the minimal surface equation. So I differentiate the u with epsilon j and epsilon k. So now, if you differentiate the complicated minimal surface equation, you will see that this wjk solves the following equation. So here on the left-hand side, you have the Schrödinger operator operating on this wjk. And on the right-hand side, as source terms, you will have terms of the form the eta, the unknown eta, which we now try to find out when applied to gradient of Vj and gradient of Vk. Vj and Vk are solutions to the linearized equation from the previous slide. There are also low-order terms, and why I call this low-order terms is the following. The low-order terms are terms which contain at most one gradient of the linearized solution Vj. I will perform an asymptotic analysis going forward. And in the asymptotic analysis, there will be a small parameter h. And it happens that these low-order terms will be smaller in this small parameter h. So when I start the analysis, I can disregard these low-order terms. Okay, so again, since we know the Dn map of the original equation, so we know the normal derivative of u, it means that by differentiating the normal derivative of u with respect to epsilon j and epsilon k, I know the normal derivative of wjk. I, of course, know also its boundary value. So I know the cosine of wjk. Cosine means the boundary value and the normal derivative. So now, when I using the fact that I know the cosine of wjk and I use this equation here above this, where we have the left-hand side is the Schrödinger operator acting on wjk. I do an integration by parts. Then I will recover or find that this following integral is known. So it has 3 terms which are symmetric in these indices 1, 2, and 3. So here we have a term. The first one is v1, and all of these v1, v2, and v3 solve the linearized equation, so the Schrödinger equation. So you have v1, then the unknown eta, which we try to find and apply to gradient v2 and gradient v3, and symmetric combinations of these. And then I will also have low-order terms corresponding to the low-order terms in the equation, as I explained. So these low-order terms will be negligible in the first layer of analysis. Okay, so what do we do? How do we find the eta? So as many of you know, there are useful solutions for the Schrödinger equation, and these are called complex geometric optics solutions. So I will choose as these solutions V1, V2, and V3, these CGO solutions, complex geometric optics solutions, and they solve this linear Schrödinger equation. And I use the form of the CGOs, which were introduced in a paper by Calderón, Guillermo, and Leo Joe in 2011. And these are solutions of the following form. So let me explain. They have a factor e to the power of phi over h, and then you have a and rh. The phi here is a holomorphic Morse function, which means that it's a holomorphic function, and it is a Morse in the sense that if it has points where the gradient of phi vanishes, at those points, the Hessian nevertheless is invertible. So that is a definition of Morse function. H is a small parameter. Also, A is a holomorphic function, and RH is a correction term, which is given by this following formula here. So it looks a little bit complicated, and you don't need to recall it. But let me try to explain what's inside it. So it's in terms of this dou bar psi minus 1 type operators. So dou bar psi minus 1 is defined. We are now manifolds, we need to somehow localize things, but it's defined as dou bar psi minus 1 acting on f, function f is dou bar minus 1, and then it acts on e to power minus 2i psi over h f. Psi is the imaginary part of the phase function. And now here the dou bar minus 1 is just the normal Cauchy-Riemann operator in complex plane. Especially it solves the equation dou bar minus 1, dou bar is the identity. Now, the form of this th here, you don't need to worry about that. It's a little bit complicated. But the main point of this RH is that this RH itself is not given as an increasing series of powers of h, as is typical in at least in higher dimensions. So RH is not of the form h times some function a1, h squared times some a2, and so on. It's a little bit more complicated. And that, unfortunately, makes the asymptotic analysis quite a bit harder. So let's plug in these complex geometric optics solutions to the known integral quantity, which was this this quantity of three guys. So I know this quantity here, and I want to pick the eta from that. So I split this quantity, this 3-component quantity, into 2 terms. So first, I will have the terms where I have this v1 hat, v2 hat, and v3 hat. And these hatted quantities are just the CGOs without the correction terms. What is left are terms which I call I other, and these are terms in this integral where I have at least one of these correction terms RK or its gradient. So now I wish to use the stationary phase for the leading order term, so this I leading, to recover eta, and I would like to consider this I other as negligible term. So now something a little bit maybe annoying happens. So if I do stationary phase for this I leading, I will have an expansion that this I leading is some non-negative constant C0 plus big O H. So all in all, this I leading is of size 1 as H goes to 0. Now the usual well-known LP estimates for the correction terms RK, they are actually O H to the power 1 over P. So what happens now is this, when you plug in this LP estimates, this I other, you will see that this I other is actually of size big O H to the power minus 1. So this is now a problem. Why? Well, this I other, which I would like to consider as negligible term, is of size H to the power minus 1, and that is much larger than my leading order term, which is of size 1. So just from these LP estimates, I cannot recover the leading order quantity, which I would like to do. So how do we solve this problem? So that is done by a little bit this kind of new type of CGOs. So now we use CGOs. The CGOs so far have had phase functions that have critical points. They have critical points that are non-determinate, but nevertheless they are critical points. So now we employ the fact that our known integral terms, such as the one you see here, this v1 eta gradient v2 gradient v3, it considers products of 3 solutions. So by using the fact that we have 3 solutions, we will choose v1, v2, and v3 to have the phases which in holomorphic coordinates look like the following. Holomorphic coordinates means that you can view things in the complex plane. So phi 1, corresponding to the phase function of v1, has minus z plus z squared plus high order guys. Phi 2 has plus z squared plus high order terms. And phi 3 will be just 2 times z bar squared plus high order terms. So now a fact happens is that with the phases phi 1, phi 2, the corresponding correction terms R1 and R2, they actually have better decay given here. So the LP estimate for R1, R2 as well, and their gradients are actually of size O, big OH. So this is much smaller than the previous estimate we had, this big OH to power 1 over P. The estimate for the correction term corresponding to B3, it is still just OH to power 1 over P. But the fact that here's this linear term in the phases, meaning that there's no critical points, gives this better estimates for the correction terms. So some of you might wonder why this has not been used earlier in other inverse problems in dimension 2. Well, the reason is now that because we have 3 solutions, I can have that these linear parts of the phases, which would, without canceling them, would cause you non-stationary phase. When we have 3 solutions, I can actually cancel them as follows. So phi1 plus phi2 plus phi3 is just 2 times z squared minus 2 times z bar squared. So this linear guys vanishes from the product of the 3 solutions. And this is now exactly of the stationary phase form, and you can use stationary phase still to recover your unknown. Yeah, so with these better estimates, we can actually have that the I other, the correct, the terms which I would like to disregard is little o1, while my leading order guide was big O1, exactly. And from this fact, I can recover the components of the 2 times 2 matrix eta, which was the second fundamental form, up to a conformal factor. So we have not yet found the conformal multiple, this C function. So how do we proceed to get this proof done? Means that we first solve completely the second linearized problem, which means that I will go to lower layers in the asymptotic analysis in H to recover the remaining quantities in the second linearization. After that, I will go to the third linearization, and from the third linearization, finally, we can recover the conformal factor by similar methods which were used in the second linearization. So all in all, we have recovered the embedded minimal surface sigma g up to an isometry from the DN map or equivalently from the areas of minimal surfaces. So the keywords from the proof. So one needs to work until the third linearization to finally find the conformal factor. I don't know an exact reason for that. There probably is one, but I don't know. Why do you need to go to the third linearization? And the second is that because the normal LP estimates for the correction terms of the CGOs were not enough, we introduced new CGOs whose correction terms had sufficient decay, and that was accomplished by using phase functions which do not have critical points. I will skip this one. So I think I'm now done. My time I think is up. So yeah, okay, maybe I read this summary still. So what we did is that we recovered the general 2D minimal surface from the DN map of the minimal surface equation, or equivalently from the areas of minimal surfaces. We also noticed that we can recover things about the 3D space. For example, in the terms that we can recover the second fundamental form. I announced the solution to, in a sense, general Calderón problem on Riemannian surfaces, where both the metric and the potential are unknown. And I used this solution in the inverse problem for the minimal surface. As well, I introduced the high order linearization method for inverse problems with rigidity type data and the ADS-CFT correspondence in physics. And this was done by using the high order variations of minimal surfaces. And the takeaway about the physics correspondence is that the entanglement entropies of the conformal field theory determine the DN map, which our community knows very well, of the minimal surface equation. And in the proof, we use CGOs without phases, with phases without critical points. And as a matter of fact, these new types of CGOs will be useful in other inverse problems of nonlinear equations in dimension 2. Now I'm done. Thank you very much.
Thank you very much, Tony, for the very nice talk. Are there any questions or comments, please? Please feel free to unmute yourself. Any questions or comments?
Hi. Yes, sorry, I have a comment more than a question, but it's maybe something that you will find interesting. And so in the billiards community, there's a very analogous problem which has to do with it's kind of like minimal surfaces, but then instead there are critical points for the symplectic form as opposed to the length functional. So there's the paper, for example, called it's Introducing Symplectic Billiards by Albers and Tebeshnikov. And there's a very related question for billiards, which is that can you recover the boundary of a domain from the area spectrum instead of the length spectrum, or equivalently instead of the Laplace spectrum? So maybe I just pointed.
Yeah. Well, thank you very much. So what was the term?
It's called symplectic billiards. So
okay.
So I mean, in a usual billiard table, just in R2, for example, if you take 5 points and then you sum together the distances between these 5 points on the boundary, then critical points of those, they correspond to this, law of equal angles. So angle of incidence equals angle of reflection. And for the symplectic billiards, instead, you take 5 points on the boundary, and then you take the normal derivatives, or sorry, the normal vector, and you add up the symplectic form with those two normal vectors. So you have omega v1, v2 plus omega v2, v3 plus, so on. And the critical points of that, what they correspond to is polygons inside the domain, which have maximal area. So instead of maximal length, it's maximal area, and they have this area spectrum. And
it's maximal, not minimal.
Yeah, well, as for the length spectrum, minus the area is minimal.
Okay, I see. Okay.
So that's it's just the principle of least action, and the action is either minus the length or minus the area.
Right. So is that some kind of, is the field in discrete mathematics or?
So it's a very new thing. I think the paper's from 2018. It's called Introducing Symplectic Billiards. And for example, I mean, one thing that we're working on now is a rigidity problem in this category. So it's, I mean, just the usual, if you preserve the area spectrum under deformations, then can you say that the deformation is trivial? But it seems very related anyway. So I thought that I should point it.
And you have papers in this business?
Wow, it was starting.
Okay, but if I search your name, I can find some references.
Sure. Or I'll email you if you're curious.
Okay, yeah, great. Thanks very much.
Thank you very much. Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Okay, if not, thank you very much, Tony, for the very nice talk. Thank you so much. Thank you very much, everyone, for coming. Thank you.